Welcome back, grade nines. In this lesson, we are going to be looking at work and power. And then the second lesson of the week, we are going to be looking at energy. So I need you to go to page 8 of your booklets. Please make sure on page 8. You should have all completed up to question 3. We did it together last time. And now we're going to carry on with work. So in this section, I want to look at how force is applied to an object or to a person, and that force is going to cause that person to move within a certain direction. So what work actually is, it's force multiplied by displacement or distance. So if someone is doing work, okay, you can define it as someone is doing work is when an object moves in the direction of the force. So let's think, for example, we've got a few pictures over here. We have a lady that's pushing a trolley. So because she's pushing a trolley and the trolley is moving in the direction that she's pushing in, she is doing work because it is moving in the direction. That is the key point. A lot of people get confused and they think, okay, if they're pushing on an object or they're pulling on an object, work is being done. No, that object needs to move in the direction of the force. So let's look at the tractor. The tractor is pulling a log. This is a horizontal component of force on the log. It's doing the work here. So the tractor is doing work on the log. Then you have this gentleman that is swinging around, looks like a yo-yo, okay? And there's tension in the string, is not working, as there is no movement in the direction of the force. There's no movement in the direction of the force. That is the most important thing, yeah? He is moving, but it is not moving in the direction of the force. Then there is a shelf. The shelf is, there'll be normal force exerted on that shelf or from that shelf, but the shelf is not moving, so no work is being done. So this is a very tricky one, guys. People get confused with this, and I need to make it very clear to you that the object must move in the direction of the force. So make sure that you're on page 8. We're going to do the definition now, and then we're going to carry on. Okay, so on page 8, there is a section for the definition I need you to fill in for me. And the work is done when a force is applied to an object and it causes the object to move in the same direction as the applied force. So make sure that you fill that in. The example that the book has is that of a pencil case. A boy pushes the pencil case, okay, and it moves in the direction that he pushes in. So the work is being done as he is pushing that pencil case on the desk. But the instant before the pencil box falls, the boy is pushing it, but it is moving in a different direction to the push. So no work is done on the pencil box by the boy. So that when that pencil box falls down from the desk, so say for example you're pushing and then it falls down, it's now falling down towards the ground. It is not falling in the direction, or it's not moving in the direction of force. So therefore, no work is being done by the boy. While the pencil box falls, the boy is not pushing it. So he does no work on the pencil box. However, gravity is doing that work. Why, guys? Because the pencil box is moving towards the ground. These are the key features of work. Work is force combined with distance or displacement. What is displacement? Displacement is a change in position. Here, it's the same thing. There's a change at the pencil box was here, and now the pencil box is here. There's a change in position. Therefore, work has been done. However, if the pencil box was here, and now all of a sudden it's falling down to the ground, and it's not moving in the direction of the force, the boy is not responsible for that work anymore. Gravity is responsible for that work. Okay. So please make sure you fill this in, and then we're going to carry on with a few formulas and a few practice. I'm sure a lot of you are asking, why are we using the letter S for distance moved? The reason we're using that letter S is later on in grade 10, you will see that sometimes we use the D letter and sometimes we use the S letter. And the reason we do that is because distance and displacement are two different things in physics. So for now, I want you just to make a note of that. Distance and displacement are two different things in physics. So please fill in your formula. It is literally work is the same as energy, guys. It's the same as energy. Why? Because what is energy? Energy is the movement of an object, okay, across a distance. That's what it is. Or it's whether that distance be it horizontal, be it vertical, be it diagonal, it is still a movement of an object or a movement of particles. Okay, so work is measured in joules. It's the same thing as energy. The two are interchangeable. Then F is force, which is newtons, and S is distance moved, which is in meters. You might Google this and come across work is equal to force over distance, and it's represented by a D. I don't want you to use the D. If you use the D, you're going to lose a mark. Make sure that you use the S whenever you apply this formula in any problem that we give you in class. Okay, grade nines, before we carry on with any sort of problem solving, any sort of calculations, I need to introduce to you the concept of power. Now, power is work over time. It's how much energy was used in a particular time. Okay, so we look at that as, let's look at horsepower. A lot of cars use that abbreviation of how much horsepower does a car have. In other words, how much energy does it expend? How much energy is it using within a certain amount of time? 1 horsepower is in 735 watts, and watts is what we use for power. That is our unit for power. And you're going to use this later on when we connect this to electricity, because power is involved in electricity. Nonetheless, let's look at the example of this bodybuilder or this guy that's lifting weights here in this example in the slide. It's asking here, in this deadlift, work does not change for a given weight. Thus, the time taken to do the work will determine the power. So remember, whenever there's time involved, that's got to do with power. This particular problem wants you guys to calculate the difference in power when the movement takes 3 seconds versus 2 seconds. How much power is involved? Let's look and see, do we have work? They have calculated work for us because they've taken the force and they've multiplied the force by the distance that weightlifter is lifting the weight, which is 0.75 meters. So let's have a look-see, and we grab a piece of paper and we can both do this together. If you look at the first one, we're going to have 2 seconds and we got 3 seconds. I want you guys to write this down, please. Write down your formula, which is power is equal to work over time. Let's look and see what is our work for the 2 seconds one. We've got a work of 367.5 divided by 2. And the answer we should have is 183.75. Let's see how much work he's done in 3 seconds. Use exactly the same work. We are trying to find how much power he's used in 3 seconds. We use exactly the same value for work, which is 367.5, but here we divide it by 3. Let's grab our calculators out. 367.5 divided by 3 is going to give you 122.5. So therefore, guys, he is definitely doing more. There's definitely more power, okay, involved in 3 seconds. More power. He has more power in 3 seconds because it's over time. So he has been exerting that energy over a longer period of time. Therefore, there's going to be more power. So make sure that you write this down as just a quick example and use watts as your unit. So it should be for 2 seconds 183.75 watts, for 3 seconds 122.5 watts. Have a look-see and we will carry on to the next section. Okay, so on page 9, you will see that there's a section there for a definition. Okay, and I want you guys to please make sure that you fill all of this in. So power is a rate at which work is done. Whenever we use the word rate, you know that there's time involved. So if I have to phrase this in a different way, I would say power is the time it takes for work to be done. That's what I would say. This means the amount of work done in a certain time. So with that weightlifter, he definitely did more work in 2 seconds versus in 3 seconds. Okay, there was definitely more power involved there. Because it was over a smaller amount of time. Below that, you will see that there is a formula for power. Power is equal to W over T. Please make sure that the T, which is represented for time in seconds, is in small t, guys. It's not the capitalized T. Power is in watts, which is W-A-T-T-S. Work is in joules, and time is in seconds. So grade 9s, in this section now we're going to practice a few calculations. You know what work is and you know what power is, and now we're going to actually apply both of these formulas, both of these concepts to the problems that are in your booklet. I'm going to show you the first problem, which is question 1. You guys need to complete up to question 6 in this lesson, and then in the next lesson we'll go through all the answers together. I'm also going to show you a calculation format, which is at the bottom of the slide over here, that might help you when it comes to very, very hectic problems that have got a lot of values and you don't know where to start. Let's look at the first question. Question 1 says an object is pushed with a force of 10 newtons and moves 5 meters in the direction of force. Calculate the work done. So what have I done here? I have now actually gone and I have put everything that I have in one section on the left-hand side. What do I have? I have force, which is 10 newtons, and I have distance, which is 5 meters. Once I've done that, it's asking, what do I need? What do I need to calculate? I need to calculate work done. So therefore, I know that work is done because the object moved in the direction of the force. So that was your keyword there. It told you automatically that the object moved in the direction of the force. So what am I going to do? I'm going to apply my formula, which is work is equal to force over distance. That's the mark already. Then I'm going to put my substitution in, which is 10 multiplied by 5, and my answer is 50 joules. 3 marks, 3 very, very easy marks. And what have I got here? I need to add my units. It's very, very important. If you don't add the unit, we are going to take a mark off. You have to add the units. So please write this under question 1. Then you will see that at the bottom I've put a calculation format. So whatever space you have to work out your stuff, work out your problem, please divide that space up so that you know exactly where everything is going to use. So use a ruler and a pencil and actually have columns for each thing that you have to do. So the first column, I want you guys to write down exactly what do I have. So maybe get a piece of paper now and write down this calculation format and that you can apply to every calculation. Before you know it, you're going to know this off by heart. The first column is going to be what do you have and what do you need to calculate. Okay, in the above example, I had force and I had distance, and I wanted, what did I want? I wanted work. I wanted to figure out how much work was done. So I'm going to write that in my first column. Then in my second column, I'm going to apply my first calculation, which 9 times out of 10 grade 9s is going to be force. So that's either going to be net or resultant force, or it's going to be gravitational force, depending on the problem. You are going to do in the second column force. Then in the third column, we could ask you for work, energy, or power. It depends. Now, if I ask you for power, and that's the question I'm asking for, or that's the final answer I want, then you obviously have to work out work first to get to power. Energy is different. We haven't done that yet, but energy and work are closely related. Okay, because they both use joules as their standard unit of measurement. So depending on the problem, you could use column 3 could be for force, it could be for energy, or it could be for power. If I'm asking for power, then it's probably going to be, you're going to put work in there. If I'm asking for energy, then you're probably not going to need to calculate work. So please write this down on a piece of paper. It's really, really going to help you grade 9s, and just implement that up to question 6 in your books. So question 6 ends on, I'm not too sure what the page number is. I think it's page 10. And then in the next lesson, we'll go through those questions, we'll go through those calculations, and then we will teach you all about energy. Okay, have a great day, and we will chat soon.